With this video, we start block number 3, which is named correlation and regression. But let me discuss first of all a little bit more general topic which is related to the whole content of block number 3. It's multivariate dataset. That's what we are going to work with in this block. Well, let's recall what data is. First of all, we represent data by some measurements or observations, and usually if the variable is quantitative, then it can be represented just by a number, right? So if you have one variable and you have a measurement for this variable for a particular individual, you get a number. The number itself, it doesn't have any dimension, it's just a single number, and usually in mathematics we call it a scalar. Or we will also call it a zero-way data. What means zero-way? It means it has no ways, no variational modes. It doesn't vary at all. And you can think about this data as a data which has a dimension 1 by 1. It means one row and one column, right? Strictly speaking, it doesn't have a dimension, but we can think about this as a little table with one row and one column. Okay, usually we don't work with single numbers. Usually we work with sequence of numbers, right? And that leads us to a vector. So vector, it's a set of numbers ordered as a column or as a row, and that's one-way data. Why it's one-way data? You have exactly one variational mode. For example, in this case, it varies from row to row, and in this case, it varies from column to column because it has only one row, right? So this data set, for example, the first one, the first vector, it has a dimension 5 by 1 because it has 5 rows and one column. And usually, in most of the cases, rows are individuals of your data, and columns are variables. So when you see a column, a column vector with 5 rows, it means it's one variable, one particular variable. Measure it for 5 individuals. For example, it can be height of 5 persons. So you have a height of the first person here, second person here, third person here, and so on and so forth. And that's exactly how we represented data in our previous 2 blocks, right? But if you have more than one variable, then you can represent your data like this, like a row vector. In this case, you have one individual and several variables. So in this case, you can see that I have one individual and 3 variables. It can be, for example, one person and then 3 different characteristics like height, weight, and, for example, shoe size of this person. If you measure several variables for several individuals, you come to a matrix. Matrix, it's a two-way data, or it has 2 variational modes because your values vary from column to column and your values vary from row to row, right? So you have like 2 modes. And that's simple because it's the same idea. You have rows as individuals and columns as variables. So in this case, it's several individuals and several characteristics for these individuals that are measured. And this is the most common type of the data that we can have. However, usually we call it this as a table, and in R we use a name data frame. So we almost never use metrics, right? What's the difference between data table and metrics? The difference is very simple. In metrics, all values are numeric. In data table, you may have a column with qualitative variables, which values are categorical values, right? So there are some words. But in metrics, all values are numeric. So if you want to turn data table with categorical variables to a matrix, you need to make all categorical variables as dummy first. Okay, but we will discuss it. Finally, you can have also 3-way data sets. You can also have 5-way, 4-way data sets. But what's the meaning of 3-way? Meaning is simple. Now you have 3 variational modes. So values vary because you have different characteristics, different variables. You have different individuals. And then there is one more mode. You can think about third mode as time. So for example, you measure something that varies in time. It can be, for example, height and weight of babies. So you have, like, in this case, 5 babies. You measure height, weight, and, for example, how big the head of these babies is. And then your third mode will be time. For example, you do these measurements every week, so you can also have variation in time. But in this block, we will work only with 2 mode data set is matrices. Most of the time it will be matrices. And that's how it looks like, right? So this is the matrix. You have individuals, it's rows. You have variables, it's columns. And then you have values. So all these gray cells you see here, they contain a numeric value. And then every value, for example, this one, it has 2 indices. It's always 2 indices. First, it's which row this value is from. And second, it's which column this value is from. It's similar to what you use in R as well for subsetting dataset. So x23 means it's a value from matrix X, from the second row and from the third column. Okay. You can also take the whole row of the matrix or the whole column of the matrix, and that will be just a vector, row vector or column vector. Okay. Let me show you a couple of examples. Well, first of all, in chemistry, we have a lot of two-way datasets as spectroscopic datasets. Let's recall what spectra are. So a spectrum, for example, if we talk about infrared spectrum, let's narrow this down a little bit. So in this case, you have wavelengths or wave numbers, right? And then you measure how much of light is absorbed at different wave numbers. So for example, you have a volume with a liquid here, you have input, so it's a source of light, source of radiation, and then you have a detector, and then you can measure how much of light went through, and then you can calculate the absorbance, how much of light was absorbed by this substance, right? And then you do these measurements for many different wavelengths, right? So in my case, I have, you can see 100 wavelengths, so you will have 100 measurements for one individual. But if you have more than one individual, so you will have a spectrum for every individual. So it means that every individual is represented by 100 values, 100 different absorbance values measured at different wavelengths. And that's naturally can be organized in a matrix. In this case, you can see that the columns are the wave number, so wavelengths in this case, and the rows are your individual substances that you did the measurements for, you made the measurements for, and then these values will be inside this, you will have the absorbance values. Okay, so this is spectroscopic data. So every row is individual spectrum, and then every column, it's absorbance of light at these particular wavelengths taken for different individuals. This is another example of the data. It's sequencing data. When you do the sequencing, you get either OTUs, the taxonomic units, or you can combine this. You can combine these OTUs into genus or genera and so on. Okay. So in this case, you can see that the values, we call them abundance. It's how often you can see one particular OTU, for example, or one particular genus. You always sum up to 100. So it means it's 100%. So you have relative abundance. So the contribution to the total abundance. Okay. And these are your individuals. So these are your samples. In this case, you can see it's different replicates. We have 8 replicates here. This is where I got this data from. And how to represent this data? Well, usually the data is represented like this. It's a table. But if you look at this part of the table, you can see it's a matrix, right? Because it's all have numeric values. So you still can use metrics to represent it. But look, most of the time, sequencing data has variables as rows and individuals as columns. So you need to transpose it. You need to turn this to swap the rows and the columns if you want to use the procedures that we are going to discuss in block number 3. Remember that everything I'm going to talk about block number 3 will assume that you have individuals and rows and variables and columns, but it's easy to swap these rows and columns. Okay. Also, you can see that this kind of data, it also looks like a table, right? Although we have all numeric data, it looks like a table. And we have a common name for this kind of data. It's called tabular data. So tabular data looks like this. So it also has the variables as columns and individuals as rows. And the difference between matrix and tabular data, you already know it. In tabular data, you may have also some of the columns, some of the variables as categorical variables. This is a data that we are going to use quite a lot in block number 3, and this is a data about people. So you have 32 persons. Half of them are males, half of them are females. You can see this is biological sex, column with biological sex, and you can see it's already coded with numbers, -1 for male and +1 for female. So -1 is male, +1 is female, okay? And then you can see that, for example, this is a height of these persons in centimeters. This is the weight of these persons in kilograms. This is hair length. It's also coded. -1 is short hairs and +1 is long hairs. We have shoe size, EU standard. We have age, amount of years. We have income, how many euro per year they earn. We have beer and wine consumption, how many liters a year they drink. And then you can see the swimming ability is just an index between 0 and 100, how well they swim. AB, it's region, -1 for Scandinavia. and +1 for Mediterranean region. So we have half Mediterraneans, half Scandinavians, half males, half females, 8 males and 8 females from each region, 32 values in total. And then finally we have IQ here. Okay. So this is very typical tabulated data. However, you can see that this data is already can be represented as a matrix because I turned all the categorical variables to dummy variables. Now you can actually tell me that we already have seen this kind of data when we had the last learning sequence of block number 2. You remember that in one way ANOVA, we represented data like this. And that's exactly tabulated data because you have categorical variable here and the response here, right? So in this case, you have 2 variables, one qualitative, one continuous. For two-way ANOVA, you may have, or for n-way ANOVA, you may have more variables. So ANOVA already is a tool to deal with multivariate datasets. You already actually dealt with multivariate datasets, right? So for example, in this case, you can see it's a qualitative, discrete, and continuous, right? But if you look at the people data, you can see that all variables in people data are numeric, right? So here you have continuous, here you have qualitative, here you have qualitative, here you have all numeric data sets, right? And then you can see that 3 of them dummy and 9 of them are continuous, right? Continuous numeric values. So that's the main difference. So in ANOVA works with categorical data. ANOVA uses these extra variables, categorical variables, to make groups. Here we will deal with multivariate datasets where all variables are numeric, and that's the main difference. So we will learn how to deal with numeric variables, how to find if there is any relationship between these numeric variables, and also how to evaluate this relationship, how to get a number that tells how strong this relationship is. So this is exactly the topic of block number 3, how to assess relationship between or among numeric variables.